So, of course, I want to thank the organizers for inviting me. It's always fun to be back in the old stomping grounds. This conference has really been sort of a unique pleasure. I was chatting with Ben about this earlier. It's rare that you go to a poster session and everybody has cavities. So anyway, it's really great to be here. I'm going to tell you primarily about work going on in my group building topological matter from light, and also a little bit about some collaborations with Dave, sort of the complementary piece to what he told you about yesterday. But I thought I'd sort of front load with the vision, because if we're being realistic, I won't get to it at the end. I think one thing we've really taken away from this workshop so far is that many-body cavity QED means many different things to many different people. I think one neat avenue, and one that I'm pushing on, is making photonic analogs of condensed matter models, right? I don't think this is the only paradigm where one can explore interesting physics in sort of a many-body, strongly correlated context. But that's the one that we're focused on in my group. And I think to some extent, one can really just ask questions about these condensed matter models in general, but I think there's also a lot to learn from the implementation process with light, as opposed to implementing with cold atoms or in the solid state, and also from the unique properties that we get from the photonic implementations. So I'm going to try something kind of new today, which is I always give this talk about, let's talk about making the ingredients for fractional quantum Hall states. And I realized that probably, at least in the Cavity QED community, many people probably don't know what a fractional quantum Hall state is. I know I don't. But so what I thought I'd do is start with a quantum optometrist's view of what a fractional quantum Hall state is, and use that as kind of a leaping off point for the remainder of this story. So just by way of background, you know, the game in general that I'm focused on is you have some solid state model where you have electrons whose properties come from some lattice of ions. When I say properties, I mean their dispersion, the behaviors of the individual particles. Okay? And then entanglement and richness comes from the interactions of these electrons. So the condensed matter with ultra-cold atoms paradigm is to explore this kind of physics where the properties of atoms are determined either by lattices or other sorts of laser beams, and the richness comes from the interactions between the atoms. And so, you know, I think some of the story of this community is to say, let's control the properties of photons with some sort of metamaterials, right? Be they circuits or microwave resonator arrays, or in our case, multimode optical resonators, and then use sort of very modern quantum optics tools to allow the photons to interact with one another. With that kind of a backdrop, that we need to engineer the single particle physics, and then we need to engineer the interactions between the particles, let's take a step back and talk about electrons initially in magnetic fields. So this is kind of the Hamiltonian for an electron in a magnetic field, either classically or quantum mechanically. And what we know is that this electron just goes in a little cyclotron orbit. So here the magnetic field either points into or out of the page, whichever one makes it go around in that direction. I can never remember which one's my right hand, so we'll leave it at that. But we would really like to understand the quantum mechanical version of this ultimately, But I don't want to diagonalize Hamiltonians with you guys, so let's see what we can get just sort of from intuition here. The statement is, if I translate this electron over a little bit in space, I get the same kind of behavior kind of wherever I put the system, right? So there's some kind of translational invariance going on. And we also know that as I speed up the electron, right, the speed of this orbit doesn't change, right? Its size changes, but its speed doesn't change. And so what we can kind of take away from this is that there's some sort of translational invariance, and also this system has discrete energy levels in a quantum mechanical context. By that I mean, I have to make up localized wave packets that move in space, but because everything is moving at this cyclotron frequency omega c, what I'm really going to have is some kind of discrete energy levels separated by omega c, and at each of these energy levels I'm going to have a bunch of eigenstates. Okay? Now, the statement is that these eigenstates are within these energy levels, these are called Landau levels. Okay? And today we're going to focus on this lowest Landau level. So remember, we could make orbitals of different sizes. If you try to do this in quantum mechanics, within this lowest Landau level, you can make sort of a minimum uncertainty wave packet, and then you can make wave packets with quantized angular momentum in units of h bar. Okay? And so the message you should take away here is, if you like math, this is this symmetric gauge representation of the lowest Landau level wave functions. And the only thing that's important is that I can write it in terms of this complex coordinate z. So if you just replace z with x plus iy, these wave functions are those objects, and everything works out. But it turns out writing it in terms of this z is going to be useful when we add interactions into the story. Okay? So far so good? Presumably everyone's seen a little bit of this in quantum mechanics? Good. Okay, so what happens when we add interactions between the particles? Well, I want these interactions to be sort of central. That is to say, they should be along the axis between the particles. That's rule number one. And rule number two is I'd like them to be, in some sense, local in space. So that is to say, as the particles move apart, the interaction energy goes to zero. So they can be attractive or repulsive. Of course, typically in a solid, they're repulsive. Now, what I really wanted to do here was give you guys a classical animation of cyclotron orbiting electrons bouncing off of each other. That turns out to be harder than I expected. So I have a lot of badly diverging numerical simulations of this produced at 4 a.m., and I just decided maybe it'd be better to skip that. So the story is the dynamics are kind of messy classically, but you can imagine situations where you get crystals with the electrons kind of going in little circles together in a classical paradigm. But what happens quantum mechanically? Well, now you can kind of create field operators for your particles if you want to work in a second quantized notation. And you can say each one of the particles that I can create has this single particle Hamiltonian, which gave me those Landau levels. And then I also have contact interactions. Okay? So for people who come from the optical lattice side, this is a familiar picture. For those who come from the cavity side, it's maybe a little less familiar. But what I'd like to do is say, if we first diagonalize this part, we get all of these eigenstates in the Landau levels. And I just want to think about interactions that are weak compared to the spacing between the Landau levels. Okay? So you might say, doesn't that mean we're in a weakly interacting limit? Well, no, because remember, all of these eigenstates are at exactly the same energy, right? And so, in fact, if I have any non-zero interaction, as long as it's larger than the 1 over the lifetime of my particles and the disorder and yada, yada, yada. Okay, so it does need to be a fairly large interaction in practice, right? But if I have any interaction in theory, it will determine the ordering of particles within this Landau level, right? Because there's no other energy scale in the problem. So the question is, if I have particles living in these angular momentum eigenstates, if I have a bunch of them, what does this term do to those particles? So oops, that was disappointing. It gave it away. So if I have a pair of particles, 1 and L equals 1 and L equals 1 and L equals 4, the statement is if you just look at what this interaction does within the lowest Landau level, well, it allows the particles to exchange angular momentum between them and move to new pairs of states. Okay? And how rapidly this happens depends upon which pair of states they started in and which pair of states they're ending up in. But you can see that this is going to get very messy very quickly if you have many particles in this system. Okay? So we've got this Hamiltonian, and then what I want to ask is, what is the ground state in the presence of that sort of short-range contact interaction between the particles? Well, it turns out Laughlin got a Nobel Prize for writing this down. And in part, it's because it's extremely simple. Okay, but the problem is that you don't have the wave functions anymore. So these things don't commute. There's a problem from Monica's talk now, which is you need the wave functions from several slides back. But I'm not going to go back to them. I'd just like you to remember that those wave functions were powers of the complex coordinate, right? That's all they were. So the statement is, if I have a bunch of electrons labeled by their index I, Z1, Z2, Z3, I can write the wave function of all of the electrons like this. Now, why is this a good way to write it? Well, it's a good way to write it because this is manifestly all particles within the lowest Landau level. Is that clear? Basically, if you expand this out, okay, every Zi is going to be raised to some power in each of the terms, right? And then it will be multiplied by this Gaussian factor. And that's exactly the form of the lowest Landau level wave functions, right? So this is explicitly within the lowest Landau level, so that's good. And there's no contact interaction. How can we tell there's no contact interaction? Well, because if Zi is ever equal to Zj, the wave function has a second order zero. Yes? And so this is a really cool thing. This is a situation where we can write down an exact solution to actually a pretty strongly correlated kind of a problem. So in the solid state, there are all sorts of interesting signatures of this, from things like fractional Hall conductivity, which is very well quantized, to evidence of fractional charge, and indeed excitations on top of this ground state that have fractional statistics, meaning when you braid them around each other or swap their places, the wave function doesn't get a minus sign or a plus sign, it can get a phase, or it can actually get a unitary, as though you're performing a quantum gate. Okay? I don't want to go into that because this is supposed to be at least partially an experimental talk. But I felt like, particularly in the context of this conference, it's quite nice to see this, because I think when we talk at the end about this kind of game of how we actually use quantum optics tools to build these states, you get some intuition for what this kind of crazy looking wave function really means. Okay, so now we can ask, if we want to explore this physics with photons, what do we need? Well, you can see we're going to need two ingredients, right? Ingredient number one is we're going to need photons that behave as though they're in a magnetic field. And ingredient number two is we're going to need some way to engineer a local interaction between photons. That is to say, if they're in the same location to an even smaller length scale than, oh boy. Okay. Even smaller length scale than the size of the modes, there's some energy costs associated with that. So we need to figure out how to kind of make these two ingredients. And to me, part of what's really beautiful about photons is that there's a tremendous amount of headroom, because they move so fast, to engineer kind of whatever single particle dynamics you want, right? And then, you know, the game is how to get these interactions. And so what I'm hoping to do in the remaining, now it's, I guess, probably an hour and 20 minutes, is, no, seriously, guys, you're going to be here a long time, is kind of give you a flavor of how that goes. Okay, so when you build materials from cold atoms, you can either think of lattice physics or kind of bulk physics. So Dave has told you about our collaborative effort using basically his tools to explore this physics in lattices, right? We make these transmon qubit arrays to engineer the interactions, and then we make these 3D microwave cavity arrays to engineer synthetic magnetic fields. And so there we've got, you know, mod insulators with ever-improving fidelity, and we can measure band structures for these lattices and edge states and chiral dynamics and all that good stuff. And so the game on this side is to put those tools together. What I'd like to really share in the remaining time today is how to do this in the bulk gas limit, where that wave function that I wrote down for you is really the nearly exact solution for optical photons. Okay, so the game is that we can use multi-mode non-planar optical resonators to make these Landau levels for light, and we can use Rydberg atoms basically distributed in the cross-section of the cavity to mediate interactions between the photons. And then, time permitting, I'll tell you a little bit about some of the ideas that we have and that we're developing with folks like Siobhan and Eric to build Laughlin states when we combine those tools. So, the basic model here that we're harnessing is that a photon in a multimode cavity behaves like a massive particle in a harmonic trap. So this is a real space analogy, not a Fock space analogy. I'm talking about a harmonic trap in space, not a harmonic trap in particle number. Okay? And so what you should really think for now is that if I have a photon and I apply this raising operator to it, I'm not putting more photons into the system, I'm changing its spatial wave function to put it into higher and higher harmonic oscillator states. Okay? So the story then is just, if you want to think from a totally classical perspective, and here when I say classical and quantum mechanical, what I really mean is particle and wave, not anything about entanglement like before. If we send light in off-axis, the claim is that it bounces back and forth between these two cavity mirrors, both longitudinally, and it also kind of oscillates back and forth laterally. Okay, so these are these ideas that Martin Weitz has employed to make photon BECs, but because we're going to also have to kind of extend them to make gauge fields, I'd like to really beat on this a little bit. So the statement is, if I ray trace and watch a photon move back and forth through the cavity, what you can kind of see is that the curvature of the mirrors prevents the photon from kind of bouncing off to infinity. It acts as a transverse trap for the light. Okay? If we want to think in a wave picture, or what one might call a quantum mechanical picture now, what we know is that the transverse modes of a Fabry-Perot cavity are Hermite-Gauss, and they're uniformly spaced in energy. That's the same as the modes of a quantum harmonic oscillator, right? Hermite-Gauss and uniformly spaced in energy. And so what this means is, if we think about a single longitudinal quantum number of our cavity, okay, there is a really nice mapping, even formally, between the modes of the cavity and the modes of a mass on a spring. Okay? And so just to really hammer this home, if I put a photon into the cavity translated laterally, kind of off-center, away from the cavity axis, I can write it state as a superposition of the lowest mode of the cavity and this first excited transverse mode. So this is like a TEM00 and this is a TEM10. Okay, and those two will constructively interfere on the right side and destructively interfere on the left side. But there's some frequency difference between them arising from a GUI phase. half a cycle later of that frequency difference, this plus sign becomes a minus sign, and now the photon is shifted off to the left of the cavity axis, right? So this, in some sense, is stuff that you know from quantum mechanics, right? And when I say it in this way, it's probably also obvious for cavity photons, but I think people often don't think of cavity photons in kind of this way. And the statement is, within a manifold of a fixed longitudinal mode in all of those transverse modes, you really have a massive particle in a harmonic trap. So you should think of the photons. These are slightly more artistically rendered mirrors. Okay, and the photon is delocalized longitudinally, right? Because as I said, a fixed longitudinal quantum number, and oscillating back and forth transversely. Okay? Great. So there's a whole flow case story if you want to understand that formally, but the sort of takeaway message is that the free space propagation along the cavity axis kind of gives your photons an effective mass, and the curvature of your mirrors provides some trapping. So the question is there a way to add on top of this a magnetic field for the light? And what I'd like to argue here is that the answer is actually yes. Okay, and that's resonator twist. Now in a two-mirror cavity, resonator twist is not a thing, right? You can turn your mirrors all you want and nothing happens. But if instead we take a four-mirror cavity, then you can twist. And the way you should think about this twist is kind of as like a periscope. So I have my two mirrors of my periscope here, and I'm looking at a tree through the periscope. Okay? The image comes out vertical. Okay? But if I rotate the lower mirror by 90 degrees, the image comes out rotated. Okay? And so the statement is kind of that the rotation of the top mirror relative to the bottom mirror produces an image rotation. And if we just take these two mirrors and add two more to kind of close the thing into a cavity, that's the kind of setup that we have in mind. All right? And so the basic aim is that then on every round trip through your cavity, your image gets rotated a little bit, and the Hermite-Gauss modes that we're comfortable with can no longer be the eigenmodes of the cavity. Okay? We can understand what the eigenmodes must be, though, mathematically, and we'll do that next. But let's just take a quick moment to think about life in a rotating frame, because that's what we're talking about here, right? We have our particle, which is massive and it's harmonically trapped, but every kind of time step, it rotates. The system looks like it rotates a little bit due to this cavity twist, okay? And that really turns the lab frame into a rotating frame. And the question is, what does that do to the dynamics? Well, you learned this in high school, probably. Middle school for the Russians. And it adds what are normally fictitious forces. In our case, they're real forces. It adds a Coriolis force and a centrifugal force. Well, we can compensate this centrifugal force with just mirror curvature. And this Coriolis force, omega cross P, looks an awful lot like V cross B, right? And so the statement is, this is really going to give us Landau levels for light when we cancel out this centrifugal force. Okay? So how does this go in practice? If you have a planar cavity, you can think of a photon trapped in this cavity as having this kind of harmonic oscillator spectrum where you can have excitations along either x or y. Okay? And as I twist it, and I'm going to show you that shortly, these eigenmodes have to mix into Laguerre-Gauss modes, basically. Superpositions of these two that are this one plus I times that one and this one minus I times that one. And when the phase winds in the same direction as the twist, the energy goes down. And when the phase winds in the opposite direction from the twist, the energy goes up. Okay? And so as I twist, what you can see is we get these ring modes, which maybe looked familiar from that Landau level story earlier, right? And we can basically make them degenerate by twisting the cavity. Okay? Now, I think in the interest of time, I'm going to hop ahead a little bit because there's a whole story about curved space here, but it's not terribly important for what we're interested in today. What's important for us is that we can make one of these cavities. It's just 4 super polished mirrors, And we, instead of adjusting the mirror curvature, we adjust the length a little bit, and that adjusts the twist, and that allows us to go to this point where the twist exactly compensates the curvature of the mirrors and gives us Landau levels for light. Okay, and so this is just sort of doing a mode spectroscopy of this cavity as we approach degeneracy, and we can make 10 modes degenerate to a megahertz or better. Okay, and that's sort of an important number because Rydberg-Rydberg interactions on the length scales of a typical cavity mode, which is 10 or 20 microns, tend to be on the order of megahertz. And so that means that our interactions are going to be larger than the disorder that comes from this cavity, and we should be able to hybridize the modes to make Laughlin states. I think, let's see. In all seriousness, I have to be done by 35 to leave 10 minutes for talking. Is that correct? Is that the game?
Yeah, aim for it.
That's what I should aim for? That sounded pretty non-committal there, yeah. How much time do I really have? An hour? No, it's fine. Yeah.
More than 40 minutes.
An hour minus 20 minutes.
What?
An hour minus 20 minutes.
An hour minus 20 minutes. I see what you did there. Okay. So we can really tune to this degeneracy point, and the cavity modes are quite degenerate. They get a little bit distorted. We think either due to mirror imperfections or some higher order aberrations in the mirror surface. But we can maintain a finesse above like 8 or 10,000, and so that's good enough for the physics I'm going to talk about moving forward. Now, so I will skip this whole story about curved space, as I said, and talk about interactions. And here's the thing that's interesting. You say 8 or 10,000, how can you possibly get into a strongly interacting regime of photons, right? If you're talking about cavities with a waist of 10 or 12 microns, right? And a finesse of 10,000, right? And here, when I say strong interactions, remember, our photons have to collide multiple times within their lifetimes in the cavity, right? And so we really need interactions which are strong compared to kappa, right? Many times kappa. And so the game is that we need interactions which are large compared to the bandwidth of this manifold of modes, which is a couple megahertz, small compared to the energy spacing to the next longitudinal manifold, right, which we want to ignore, which is a couple of gigahertz, but that'll be no problem. Yeah, don't worry about that. And they need to be large compared to this kind of megahertz energy scale when the photons are within kind of a magnetic length or kind of the size of a mode of this cavity. Okay? And remember, we can only think of the physics as kind of living in this central plane because the light is sort of continuously refocused by the cavity mirrors. So this is kind of a bizarre thing. If you look over here, this is momentum space, or almost momentum space for the light. So if you put a medium that mediated interactions over here, you would have like momentum space interactions. And if you put the medium here, you get real space interactions, right? And so what you don't want is a medium everywhere, right? Because then you have some kind of weird hybrid of real space and I mean, maybe you do want that. But for this, I mean, I think that's actually, it's an interesting question, right? For this community, we can make models that basically have no analog whatsoever. I mean, look at this stuff that well, maybe they do have analogs, but they're crazy analogs, right? That bend stuff. And so I think, you know, embracing that is maybe a good thing, but a piece of the game is that we have the freedom to go either way. And here we want the interactions to be local. So we need to put some medium here, which enables the photons to collide with each other in real space. And to understand the medium that we're putting in, we should think about what happens when light goes into any medium, okay? The basic understanding that you should have is that why does light slow down when it goes through a piece of glass? Well, light always moves at the speed of light when it's light, right? But when it's been absorbed by an atom, it doesn't move at all. And so the index of refraction is sort of a reflection of the fact that your photon is spending some time as an atomic excitation as it moves through the window. Yeah? So the game here is to create a situation where when the first photon goes into the medium, it excites an electron up to, say, a very highly excited state. In our case, we're going to go to n equals 100. Okay? And what that will do is basically create an electronic orbital in here, which is many, or in the neighborhood of a wavelength across. Okay? And so what that means is when a second photon tries to go in and get absorbed by those atoms, the atoms can't absorb it because of the interactions between the electrons. Yes? So if the second photon gets near the first photon, this object looks transparent. Right? And that's sort of how you can think about Rydberg EIT. The first photon creates a spatially varying index of refraction for the second photon, and the second photon can then lens off of that. Okay? And in the appropriate language, that's really a collision between your photons. So this idea was pioneered by Misha and Laughlin in this pretty cool paper. Actually, it's a very cool paper. Let's not undersell it. We are in Cambridge, after all. So what we're trying to do is take these ideas and move them into a multi-mode regime, multiple transverse modes, and also into a cavity, because we've got this great setup where we have magnetic fields for light. And so all we need to do is combine that with these interactions. Okay? And so what you should then think of is your photons are moving back and forth transversely, right? And you create a superposition of a cavity photon and an atomic excitation that kind of follows it around. Okay? And for the experts, we get a collective enhancement in the interaction between the photons. We don't have to think about the single particle cooperativity. We can really use the n particle cooperativity, because all n of these atoms, which have sort of changed color, can only be excited once in total due to this Rydberg interaction between the atoms, right? So these n atoms that are moving around together really sort of effectively act like one atom. Okay? So in practice, what we do is we build a 4-mirror cavity like this. The separation between these two mirrors is about 2 centimeters. These two mirrors are actually convex, and this is a cool geometry because even though these mirrors are 2 centimeters apart, we get a waste of about 11 microns in between them. Okay? You can think of this as kind of a tie-saft kind of a cavity. We take a mott, we load it into a dipole trap, which we convert into a lattice, and transport the atoms up into the cavity. So now we've got a cloud which is about 100 microns long, which is large compared to this kind of blockade length scale. And so what I'm plotting here is the cavity mode as it propagates through the atoms. And what we need to do is use some kind of super resolution technique, which if you want to chat about, we can talk about later, to slice this cloud down until it's about 10 microns thick. Okay? And now we can perform Rydberg EIT experiments. So first we can see the atoms move through the cavity. That's all very nice. But if we add a beam that dresses up to this Rydberg state, we not only get a vacuum Rabi splitting, but we also get this electromagnetically induced transparency window in the middle, where when photons go in here, this window is very narrow, which kind of reflects that the photon spends a lot of time as a Rydberg excitation in the atomic gas. Okay? So we typically get a ground Rydberg coherence. Now we're down to about 50 kilohertz. Remember the interaction energy scale between these Rydbergs is about 10 megahertz on the length scales that we're talking about. And so this is kind of the latest and greatest cavity here. It turns out you need to keep the mirrors very far from the Rydbergs because Rydbergs hate everything. You want things that are extremely sensitive to electric fields, but you can see the chemistry of things getting adsorbed onto the surface at a few millimeters away, just because a few millivolts per centimeter field is enough to make your Rydbergs very unhappy. So anyway, Nathan Shine actually worked extremely hard on this. This is also the guy who did the twisted cavities. So compared to the twisted cavity, this was actually very easy for him. Now he's trying to make a twisted version of this, and that's not so easy. But anyway, when you look at this, this is now looking at Rydberg EIT to this 100S state. And what you can see is that you should be able to put one photon into this cavity, but if you try to put a second one in, it'll reflect off. And once that second one leaves, or the first one leaves, you should now be able to put another one in. And this should be reflected in a power dependence of your transmission. As we increase the probe power, the transmission drops, okay? And that should then be reflected if it's really a single photon nonlinearity and a suppression of the G2. Which we actually see here quite nicely. And in fact, we can even drive or start to drive Rabi oscillations on this dark polariton resonance. So basically the system Rabi oscillates one polariton into the cavity and back out and so forth. And this dark polariton number really saturates at 1/2 at high drive powers, which is evidence that this is really effectively a two-level system here. So this is the kind of single transverse mode version of this story. And the game moving forward is to apply these ideas in a multiple transverse mode paradigm to make Laughlin states. And so what I thought I'd do with the last couple of minutes is kind of try to give you a flavor of how we will combine these magnetic fields with photon-photon scattering to build what I call here optimistically topological many-body states. Maybe you call them topological few-body states. People call them Laughlin states. We call them Laughlin droplets. Because it will not be a huge number of particles, but I think we can kind of get some neat intuition from the way that this works. So the experiment that I just described to you says if you have interactions between your photons in real space, and you inject into the L = 0 mode of this cavity, you should be able to put one photon in, but you won't be able to put a second photon in, right? Because of this photon-photon interaction. So the second one will reflect off, right? And I showed you data for that. But, so now here's the question. What if I inject into the L = 1 mode of this cavity? Well, you would say the photon-photon interaction should still prevent me from putting two photons into the system, right? But remember this squeezing rule I told you about earlier, right? The interactions conserve angular momentum, right? So if there's no angular momentum state in the Landau level below L = 0, two photons in L = 0 can't collide and go into a different pair of states. But L = 1 photons, if there are two of them, they can collide and change their angular momentum, can't they? Right? So two L = 1 photons can collide and turn into an L = 0 photon and an L = 2 photon. So this is a kind of a cool thing, because now there's the question is, you know, we have three different states, or three different terms in this two-state manifold to think about. There's an interaction energy cost associated with having two photons in L = 1. There's an interaction energy cost associated with having a photon in L = 0 and a photon in L = 2. And then there's an interaction matrix element which couples those two states. Okay? And so the question is, what superposition of these two states has the minimum Rydberg interaction? Well, the answer is it's the one with a minus sign there. And you can rewrite that as Z1 minus Z2 squared times this, which hopefully you remember from the beginning of the talk as the two-photon Laughlin state, right? And so the way you can see this is that this state is superpositions of terms that look like Z1 squared times Z2 to the 0. That's one term in L = 0, one photon in L = 0 and one in L = 2. And terms that look like Z1 to the 1, Z2 to the 1, which is both of the photons in this state. Okay? And so what this means is you can kind of think of this system as a Laughlin state filter. As long as the state with a plus sign here has a large interaction energy, when I inject on L = 1, two photons will come out in a superposition of L equals 1 and L equals 0 and 2, right? They come out in the two-photon Laughlin state. And indeed, the theory says if you do this on L equals 2, 3 photons will come out in the L equals 3 Laughlin state, and so on and so forth. Now, in practice, the scaling of this is not so favorable, basically because 3 photons in L equals 2 doesn't have a great overlap with a 3-photon Laughlin state. And so there's a real game of what are better ways to build and stabilize these sorts of states. So one idea is to harness this dissipative stabilization technique that Dave talked about yesterday for Laughlin states here. And guys like Jacopo Carasotto and Mohammed Hafezi have thought along these lines. And another kind of possible approach to making these states is to Thouless-pump, basically put a photon in and then flux thread the system. I didn't tell you about tones, so maybe we don't talk about that one. But a kind of cool idea that Eric and Chauvin have been thinking about is if you first inject a photon in L equals 0, and then you next inject a photon in L equals 2, right, that should also have, as the only non-interacting state, the 2-photon Laughlin state, right? And then when you inject again for the next one in L equals 4, well, you're not going to end up with photons in 0, 2, and 4. You're going to end up with photons in the 3-photon Laughlin state. But because you're kind of growing at the edge of the system, you know that the system has, a good overlap with adding a particle there. And so it's kind of a good way to build up the many-body states, potentially. But I think there are all kinds of different approaches that one can think about for exploring building of these states and stabilization of them, which is kind of unique to the fact that we have as many photons as we want as a resource, and in a way that can be kind of tricky in a cold atom experiment, right? So photons are real cheap. Although I guess it's an interesting question. Are photons cheaper than atoms?
Yes.
Yes?
Yes.
No? Yes?
That's pretty expensive.
Yeah. It's a fair point, but yeah. So anyway, I guess with that, I'll conclude. I do want to thank my whole group and particularly highlight these folks. Alex, as Dave mentioned, is the real superstar leading this quantum circuits mod insulator effort. And he's really fantastic. He comes from Marcus's group and in a year went from knowing nothing about quantum circuits to building an 8-qubit quantum simulator. Nathan is the twisted cavity expert, and Michelle worked closely with him. We have some churn number measurements for these Landau levels that she performed. She's actually now here, Michelle, working with John Doyle. So you should all say hi to her. I can wait. No? Okay. And actually, John, Nathan have really been leading this Polariton effort, and Clay is making the gauge fields for the microwave photons. So and of course, Dave's pretty great too. And this is our logo. So with that, I'll thank them and thank you guys for your attention.
So you're talking about how the angular momentum has to be conserved in these photon interactions.
Mm-hmm.
Is there any reason you shouldn't expect any angular momentum to go into the atom cloud rather than just the string photons?
So it's an interesting question. The simple answer is you can do the calculation, and the answer is that it doesn't.
Is that making some approximations, or is that
Always.
I mean,
But it's making good approximations. No, but I'm trying to think about the good way to think about this is that the laser beams are basically longitudinal, right? It is a piece of the story. Oh, actually, a better answer has to do with the recoil of the atoms, right? The energy scale associated with the atoms getting the angular momentum is very, very small, right? And so what that means is that will eventually happen, right? But on timescales very long compared to these experiments. Remember, the polaritons live for at most a microsecond, so atomic motion doesn't end up being a big thing on those timescales. When we can get the polaritons living for a millisecond, then we will happily put the atoms in a 3D optical lattice. But that will be the least of our worries at that point. Good question.
Yeah. So this went over pretty quickly, but you said you showed these nonlinearities, and then you said that Rydberg is like a two-level lab, but there were very interesting dynamics going on.
Yes.
So what are the origin?
So you're saying what's this fast stuff at the beginning?
Yeah.
So maybe we should talk just briefly about what we're seeing here. Without this fast thing at the beginning, you should think of this as I'm driving this polaritonic mode, and it can absorb a photon and then be de-excited, right? And if this were a linear system, it would just keep absorbing and absorbing photons, right, and just reach a steady state. But because it's a nonlinear system, even when you drive it on resonance, it oscillates, which tells you that it can only absorb one excitation, and then it gets de-excited. So then you ask, but what is this really fast thing at the beginning? Well, the statement is, if you want to see these oscillations, you have to drive this thing hard compared to its width, right? Otherwise, the oscillations get damped out. But when you start to drive this central feature harder and harder, remember, its height is, in some sense, kind of fixed. This can only absorb one photon, right? How many photons can these bright polaritons absorb? As many as you want, right? Because these correspond to excitations of the atoms to the p state rather than to a Rydberg state, right? And so what that means is that while this rapidly saturates at one excitation, this off-resonance excitation, which at lowest order is very strongly suppressed, when you drive hard, just continues to get bigger and bigger. And so this fast oscillation here is the off-resonant excitation of the bright polaritons.
So it only shows up when you do resonant two-photon transition, but not detuned.
Yes, so you might say, why don't we detune from the p state? And the answer always in these experiments is that optical depth, even collective optical depth, is at a premium. So as you detune from the p state, you either need a tremendous amount of blue power, right? Or you need a tremendous optical depth, or probably both, right? And so to get the best nonlinearity, you work on atomic resonance.
Do you have to think carefully about what Rydberg states you use to do this?
Yes. Yeah, so I think this is actually a really interesting question as well. If you go to too high a Rydberg state, your interaction range is large compared to your magnetic length, and you can't think of the things as contact interactions, right? And even though you still get conservation of angular momentum, right, because it's a central potential, you don't get the right form of the interaction such that this quadratic suppression of them being close together is enough, right? And so as a consequence, higher Haldane pseudopotentials come into the story. But so you don't want to go too high in principal quantum number, but if you go too low in principal quantum number, your interaction becomes small compared to the lifetime of the particles. So there is kind of a sweet spot in there where you get the best behavior. None of this stuff is really truly universal, but it's universal over some parameter range.
I have a question up here.
Yeah.
John, so if I forget about Laughlin states, or when I try to understand in real space what's happening when your photons collide at the conserved quantities. So I mean, I have this first photon that gets absorbed that corresponds to some coherently distributed excitation, right, in the atomic sample, and then I have this second photon that arrives in different spatial mode, and then what?
Sorry, for the Laughlin state story. Yes?
For the photon-photon interaction and in terms of what quantities are conserved.
So they're okay, for the photon-photon interaction in the multi-mode case, yes? So there you say the first photon goes into the L equals 1 state of the cavity, and the atomic ensemble gets excited into a collective excitation, which is also in the L equals 1 state. Okay? When I try to send a second photon in, it cannot just go into that L equals 1 state, because then there would be a large energy cost associated with that. Okay? So what happens is both photons rearrange. Okay? And I end up in a situation where I have a superposition of both photons in L equals 1, or one of the photons in L equals 0, and one of them in L equals 2.
Yeah, but in reality, at that stage, it's an atomic excitation. So
No, but it's both. The point.
So how does it redistribute? That's what I.
So the statement is as long. So what's the best way to describe this? Let's talk about just two spins. Okay.
Is there anything moving in real space at that time?
So the photons are moving. The atoms don't move. It just changes which atoms are excited. Right? And it's actually a very interesting thing. The requirement for all of this redistribution to happen is real strong coupling between the light and the matter, right? It all scales fundamentally with the square root of the collective cooperativity here. Because essentially what happens is, for that to happen, the excitation has to Rabi flop back from this atoms into the cavity and back into a different atomic distribution, right? But the point is that as long as this splitting is large, right, compared to the interaction scale, when you try to make the photons redistribute, the atomic distribution automatically follows it, right? And so this is why you can kind of prove that the optimal number of collisions between photons you can get is the square root of the collective optical depth, right? And so what this means, or within a blockade radius or not. And so what this means is that really you optimize your interaction strength and your dark state rotation angle and blah, blah, blah to get to that root optical depth scaling of the number of collisions within the lifetime of a single polariton. Does that answer, more or less? Okay.
So John, is there any interesting story with the dispersive part of the EIT? The fact that your dispersion of a slow light.
So, sorry, you're saying does that play any role?
Yeah.
So, it's actually kind of neat. I told you that the photonic modes have to be degenerate to less than the interaction strength. But that was a lie. Because what happens in practice is that the polariton spends most of its time as a cavity photon, or as a Rydberg atom, right? And so the way you think about this is that you can say the mass of the polariton gets renormalized compared to the photon mass if you want. But really what it means is that if you have a spectrum, a single particle spectrum for the photons, when you couple to the Rydbergs, the spectrum gets compressed by the sine squared of the dark state rotation angle, right? And so, I don't know if that's what you were asking, but yeah, that's what happens in practice. And it just has to all fit within your EIT window. Good to see you.
Can you combine
Thanks.
them and create some subway plane structure? By the way, since
Julian yesterday, is there entanglement?
Yes. Yes, absolutely.
Oh, yeah, sure.
Between LG
Basically,
Well, you can think of it.
mode entanglement.
You can think of it either between the modes or between the photons, but it's honest to God. I mean, look,
It has
the
to be
Laughlin
entanglement.
state, the Laughlin, so this is the
Laughlin state's like an entanglement state.
no, it's a funny thing. In the large n limit, the entanglement doesn't scale very strongly, but then you probably know better than I. The entanglement of a Laughlin state. I mean, I think it's basically, an area log, it's not a dollar. But the Laughlin state is definitely an entanglement.
And for you to see the things you want to see require
Yes. So this is why I say you can have how many collisions can polariton get within its lifetime. right? So that's this Resonator, right? And the reason there's an N in there is otherwise it would be something that you think
This is something that also accelerates. You just think of, you want a wave function